A very good morning to all of you. Today I am going to discuss about different concepts and applications of urban growth models. Yesterday we have discussed about urban growth, urban sprawl, what are the differences between urban growth and urban sprawl, and what are the factors that are responsible for urban growth and urban sprawl. And it is also discussed that for studying the urban growth or urban sprawl, we need to first see the landscape dynamics. We first need to study the changes in land use, land cover over that study area. Okay. So in the last class, we have already discussed that. Quickly, I am going to describe some basic facts about the land change models. Land change models, or you can call it as urban growth models. Okay, because urbanization is directly related to the change in the landscape or change in the land use, land cover. So we can normally termed as land change models. Okay, but in broader way, or you can say for a specific point of view, you can call it as a urban growth models. So all the land change models are the tools that is used to support the analysis and causes of the landscape dynamics. Whatever the changes in the landscape, how many changes are there. Okay, so the land change models are very much useful. These are some tools that is used to support the analysis of the causes and consequences. What are the causes for that kind of dynamics in the land use, land cover, and what will be the consequences of that land use, land cover dynamics. Okay, so the scenario analysis. Scenario means we need to define some scenario. Scenario may be different variables, it may be different factors, different constants. So the scenario analysis with land use change model can support land use planning and policy. So depending on the past trend, we can go for the future scenario, future prediction, and that information will be very much useful to support the planning and policy in the near future related to urban planning, or when you are going for a sustainable urban development, sustainable urban planning. So most of the land change models are capable of capturing different aspects of the complex dynamics. Okay, because this land use dynamics, or you can say the changes in land use, land cover, are very complex phenomena. It involves several factors, it involves several variables. Okay, so the models can easily capture different aspects of the complexities of the dynamics in land use, land cover. That can also help to support the important factors, important variables during these kind of landscape dynamics. Okay, so these are already known to you. We have already discussed in the last class what should be the characteristics of a good land change model or good urban growth model. It should be spatially explicit. Spatially explicit means it should have some spatial information and quantifiable. It should be spatial information. It should be enabled with some spatial data sets, spatial coordinate system, and it is very much possible to have some quantitative information by using that land change model. It should also be able to examine the total landscape, okay, and the urban growth in all areas. It also maintains the spatial pattern and configuration. Spatial pattern means the distribution of different spatial features, including agricultural land, forest, vegetation, water bodies, built up, anything. So land change model should maintain the spatial distribution and pattern of different earth surface features and their configuration. It is also possible to display the emergence of growth over the time, and it should also include some historical data. Means what was the past trend of that urbanization, what was the past trend in the landscape dynamics. It should also be incorporated in a good land change model, and it should be intuitive, it should be interpretable and easy to calculate. Whatever the results or whatever the models we run, it should be very easy to calculate. It should be the interpretable. Whatever the results provided by the land change model should be interpretable, and it does not require much data input. So these are some characteristics that a land change model or that a urban growth model should have. Okay, so the land change models, wait, yeah. So as we know that most of the changes in land use, land cover, or the dynamics of land use, land cover, having some factors behind that. Whatever the changes is there, there may be several kinds of factors. The factors may be socioeconomic or biophysical factors. These are known as driving forces or driving variables. It is already discussed. These are different kinds of driving factors. It may be any kind of infrastructure extension. It may be agricultural extension, wood extraction. Okay, there may be some socioeconomic factors that are behind that land change model or urban growth. It may be some economic factors, it may be some technological factors, policy and institutional factors may be responsible for landscape change or landscape dynamics. Cultural factors may also be responsible for the changes in the land use land cover of that area. So these are some common type of variables, or you can say that these are the driving factors. These are the driving variables that may be responsible for different processes and different phenomena over the landscape, or you can say the urbanization, urban growth, or landscape dynamics, whatever you use the term. The main theme is that we are studying the dynamics over the time period of any study area. So there may be several factors. There may be only one factor, or there may be several factors, but we should consider the entire factors that is possible to have in that study area. Okay, so this is already discussed that land change modeling basically establishes a statistical relationship between different variables. Okay, if we are talking about more than one variable, so how a variable is related with another variable, and how the relationship between different variables are affecting the landscape of this study area that is under study. Okay, so it includes non-spatial and spatial analysis. Okay, so the amount of change, whatever the changes are there, how much change is there, that can be done by non-spatial analysis. Whereas the location of the change, where the changes are occurring, what are the location of the landscape change, it can be done using a spatial analysis. So we need to perform spatial and non-spatial analysis both for identifying and for quantifying the driving factors or driving forces. Whatever the changes are there, that can be used for getting the land use demand, and where are the changes are going, that will be considered to as a land use allocation. Okay, so the urban growth models are used for the prediction of land use land cover changes. Okay, whatever the changes in land use land cover, uh, in basically the urban growth is directly or indirectly affected by the changes in land use land cover. So when we are talking about urban growth models are mostly used for the prediction of land use land cover change. And the land use land cover modeling is extremely difficult due to complex interaction between multi-scale factors, because several factors are interacting with each other. So there may be the complexities between different factors, different driving factors, different variables at different scale. Okay, so land use land cover images of two distinct time. So for that, for urban growth modeling, we need to have land use land cover images of two different time periods. Okay, and the probabilities are computed using the frequency of the changes from one LULC class to another LULC class. This is known as transition probability matrix. We have the LULC of two time period, that is, for example, say 2000 2020. So we will calculate the probabilities of the transition among different LULC categories. That is known as transition probability matrix. Transition probability matrix is a kind of matrix. It is a two-dimensional matrix having rows and column that provides us the information about the probabilities of the change of one LULC class to another LULC class over the period of time, whatever the study period you are going to study, 10 year, 20 year, 30 year, 40 year. Okay, so Markov chain model is very much important for analyzing this kind of land use land cover changes. It predicts the quantum of the growth along with the rate of transfer. Markov chain model provides us the quantitative information about the LULC changes. Whatever the probability we are going to calculate, the probabilities of the change of one LULC class to another LULC class will be calculated, will be quantified using Markov chain model. Okay, that Markov chain model just provides us the quantitative information of that LULC transition over the period of time. Okay, and after that we can have different models, cellular automata model and logistic regression models that are effectively used to model the spatial geographic process. So Markov chain provides us the probability, and after getting the probability of the change of one class to another class, we can have different other models, cellular automata, logistic regression, neural network model. These models can be effectively applied to model the location of the change, for model the spatial information of the change. Okay, so this is the systematic diagram of how we are going to use Markov chain and cellular automata logistic regression model for land use and cover change. So first we need to have a Markov chain model. The Markov chain model provides us the probability of the transition among LULC classes. Then it will be that this information will be provided to the cellular automata and logistic regression model that will be used to predict the land use land cover change. So during this, we also need to have some spatiotemporal factors. Factors, whatever I have discussed in the last class, like there may be temporal factors, spatial factors, or spatiotemporal factors. So out of three factors, spatiotemporal factors and spatial factors are direct factors, whereas temporal factors are indirect factors. So here we are generally considering the spatiotemporal and spatial factors. These are the direct factors. These are the direct responsible factors for any kind of change in LULC in any study area. Okay, yeah. So but the Markov chain model having some limitation. Okay, because Markov chain model is built only for the cross tabulation of transition. Markov chain model only provides us the transitional information, probabilities of the information from one class to another class. Okay, and some elements of the transition probability matrix for the future time period are derived based on the simple power law. When we are talking about the transition probability of one LULC class to another LULC class, it may be persistent. Okay, because in some cases there may be no change. Okay, so in that case the persistent rate of the change may be some limiting factor when we are going to use Markov chain model. Okay, so temporal factors may be well known, the processes such as LULC change and socioeconomic changes. Okay, so we can link the LULC changes with the socioeconomic changes. These socioeconomic changes are considered as the temporal factors, and Markov chain model does not allow incorporation of the temporal factors. Okay, when we want to integrate, when we want to incorporate socioeconomic factors, the Markov chain model will not allow you to, will not support to add, to incorporate the macroeconomic factors or socioeconomic factors. So for adding more socioeconomic factors, for adding more biophysical factors, driving factors or driving variables, we need to use several other models, that is cellular automata, neural network, logistic regression. Okay, Markov chain only provides you the quantitative information. So this is the entire modeling framework. So in the modeling framework, we need to have two basic components, quantity and location. Quantity means how much change is going there and what is the location of that change. The driving factor of LULC change is known as quantity at time t, whereas the driving factors of land is land cover change location at time t is the location of that change. So two important factors in a modeling is how much change is there and where the change is going on, where the change is occurring. So by identifying or by getting the information about the amount of change and the location of that change, we can use is at a demand and potential. Demand means the rate and magnitude of the change of each LULC class at time t. How much change is there? What is the rate of the change? What is the magnitude of the change? It is known as demand. Okay, and where it is going on? What is the location of that change? It is known as potential. So how much and where? How much provides us the information about the demand, the rate of the magnitude, the rate and magnitude of the changes. Where provides us the location, where it provides us the potential site, potential location of any kind of change. After integrating both the information, the amount of change and the location of change, or we call it as a demand and potential. When we incorporate the information from by demand and potential, okay, then we can go for the allocation of the change that combines both the demand and potential, that is known as allocation. Okay, by integrating the amount and location, we can have uh, improved information of the allocation. That allocation have both the information, amount of the change and location of the change. That information will now be used for modeling purpose. It will provide you the land use map at subsequent time period after 30 years, 20 years. Okay, and also during this process, during the process of the allocation, we need to also have some spatial drivers or driving factors. You need to also identify the driving factors during this process, because when we are going to allocate the location of the change, so what are the factors behind that change, how there is change, in what way the change is there. So you need to identify the factors, you need to identify the driving variables behind that much of change in that area. Okay, so by integrating all this information, we can have the complete information about the amount, the location, and the responsible factors, the factors behind that change in that study area. So you will get the output, you will get the future landscape scenario based on this information. Yeah, this is the way in which we can have the demand. Demand means change. Okay, how much change is there? You can quantify this change over the period of time. So there is a thematic map, there is thematic information of two different time period. You can see, you can clearly see the changes. The red patch is increased after few years. So how much increased information is there, how much classes is changed, what is the amount of the change over different period of time. It will provide you the demand, means it is the rate and quantity of the change. This is simple demand model. The potential means where is the change is going on, what is the location of the change. Okay, if there is change, definitely there should be some location, there should be some you can say the most probable location where the change can happen, where the change is going on. So for getting the information about the location of the change, we may have different driving factors. Driving factors will tell you that at that position, at that location, there is a change, and that is known as potential. So two terms are there, demand and potential. Demand provides us the amount of the change, potential provides us the information about the location of that change, where the change is going on. Okay, and during this process, during the process of the identification of the location, we will incorporate several driving factors. Several driving factors may include socioeconomic factor or biophysical factors, and all this information will be integrated in the neural network or any other model to get the output. So here you can see x1, x2, x3 are the input variables. It may have two different LULC classes. It may have different driving factors, different driving variables. And when we put all this information into our model may be cellular automata, it may be neural network, it may be logistic regression. When we integrate, when we enter all this information into the model, we will get some output that will be the future landscape scenario, that will be the location of the change in the future time. Okay, so I will show you a case study. Okay, but first we need to know more about different kinds of land chain simulation or land chain prediction models: Markov chain, cellular automata, and multi-layer perceptron neural network. Okay, Markov chain is a simple model that describes the states of the system at successive time. Okay, it provides us the quantitative information, it provides us the probability of the change of a class from one time to another time. Okay, so this probability is known as transition probability. Transition probability matrix I have already discussed. Transition probability matrix provides us the probability of the changing of a pixel of a class into another class. Okay, but Markov chain ignores the driving forces and the spatial distribution. Markov chain only provides us the quantitative information, but where the change is there, where the change is going on, and what is the driving forces behind that change, it will not be described by the Markov chain. So for that, we use another model, that is cellular automata, and we integrate cellular automata with the Markov chain model. So it will have quantitative information as well as spatial distribution of the changes, because cellular automata and neural network can easily integrate the spatial distribution of the changes. So Markov chain only tells you the quantity, only tells us the amount of the change, but where the change is going on, that will be incorporated, that will be studied, that will be analyzed by using cellular automata and neural network. So cellular automata and Markov chain can be integrated with each other. Cellular automata is a dynamical discrete system in space and time, okay, that operates on a uniform grid-based space. It consists of the cells. Cells means pixels. All the image is made of small pixels, small cells. So in case of cellular automata, it consists of the cells and simple transition rules, that is automation, that are applied to determine the state of a particular cell. Suppose here red pixel, this is a cell. So this red pixel is surrounded by some other pixels. So what is the probability of the changing of this red pixel into any of the surrounding pixel? It will be calculated, and its spatial distribution will be described by cellular automata. So cellular automata adds the transition rule depending on the neighboring pixels. If this red pixel is agricultural land, if this red pixel is agricultural land, so there is a possibility that the surrounding pixels will be agricultural land, or you can say this red pixel will be converted into another class surrounded by it. Suppose these all green pixels are, suppose you can say, vegetation, and this red pixel is agricultural land. So if it is surrounded by all the vegetation pixel, so there is a possibility that this red pixel will convert into the vegetation in near future. So cellular automata adds, cellular automata incorporates this information based on its surrounding pixels. The central pixel will be affected by its surrounding pixel. So there are 4 different ways in which cellular automata selects the central pixel and surrounding pixel or neighboring pixels. So von Neumann, in von Neumann, the central pixel will be surrounded by 4 neighboring pixels. Moore method, in Moore method, the central pixel will be surrounded by, you can say, the you can say all 9 pixels. Okay, then in von Neumann, it is also having the central pixel, that is red pixel. It is surrounded by this much of another pixel, the pixel of other class. And this Moore also having different mechanism, different phenomena, different condition to select the neighboring pixels. So it may have any of the condition. It may have any of the condition depending on the complexity in the study area, depending on the complexity in the land use line cover. Generally, it works in 2 different ways. That is first 2, 4 pixel and 9 pixel. Okay, but on the basis of the complexities, in case of more complexities, it may have different other ways to select the central pixel and neighboring pixel in this way. That is von Neumann and Moore. Okay, so cellular automata calculates, cellular automata works on the principle that if there is a pixel and it is surrounded by some neighboring pixels, so what is the probability of that central pixel to be converted into the pixel of different class surrounded by that? Okay, that is the way in which cellular automata calculates the probability of the central pixel to be converted into any of the surrounding pixel. Maybe the central pixel will have different types of other classes, but Cellular automata calculates which is the most probable condition, which should be the most probability of the changing of the central pixel to the neighboring pixel. So this is the way in which cellular automata calculates the probability of the changing of a pixel surrounded by the neighboring pixels. Okay, this is cellular automata method. Another important method is multi-layer perceptron neural network method. Multi-layer perceptron is a kind of neural network method, and it is trained by backpropagation algorithm. Okay, and it is very important to note here that multi-layer perceptron neural network method can run the multiple transitions. Multiple transitions means, as we know that if we are talking about 5 language land cover classes, and we are talking about 2 different years, 2000, 2010. Okay, so there is a possibility that each LULC class will convert into another LULC class. There may be multiple transitions. It's not like that ki only agricultural land is converting into built up, or only fallow land is converting into built up. There may be other transitions. So there may be multiple transitions at a time. So multi-layer perceptron is a type of neural network that may have the ability to have several inputs. These several inputs may be different types of transitions among the LULC classes. Okay, so the input layer, the neural network having 3 components: input layer, output layer, and hidden layer. Under input layer, we may have 2 time period LULC classes, different kinds of transitions between the LULC classes, different variables, different factors, all can be added in the model using input as a input. Okay, so in multi-layer perceptron neural network, it is integrated with the Markov chain. Markov chain only provides us the quantitative information, but if you want to see the location of that change, so we will go for the neural network. Neural network provides us the facility, neural network provides us the ability to incorporate all the input variables to see the location of the change, to see the locational information of the change in various land cover classes. Okay, so it is a hybrid approach because it is integrating 2 different methods, MLP and Markov chain. So it's a hybrid approach that is used to quantify the transition by the Markov chain and or modeled using the neural network. It may also combine the variables. Variables may be socioeconomic, the variable may be any biophysical variable. Depending on the availability of the LULC classes, depending on the different variables affecting the LULC transitions, we can use this kind of multi-layer perceptron Markov chain model. So these are 3 basic models: Markov chain, then cellular automata, and multi-layer perceptron neural network. These 3 models are a very important and very useful land change model or urban growth models. By applying these 3 models, you can easily go for the urban growth modeling. So moving to the next slide, I'm going to show this you guys a case study. So this is a flow chart of a case study. Here in this case study, we have chosen LULC over 2 time period T1 or T0. Okay, then we have also defined different explanatory variables, that is driving variables. Okay, these driver variables will be selected for that model and after integrating that variables into the model, we can have the potential sites, we can have the land use suitability. Land use suitability means the potential site of the change, and that potential site of the changes will have the spatial allocation. And now we are also having the quantity of the LULC change, that is demand. This quantity of the LULC change is demand. So demand is integrated with the allocation, and here the potential, the information of the location of the change is also integrated with the spatial location. So this spatial location will have both the information: land use suitability or the potential site of the change or the location of the change, and quantity of the change, that is demand, the rate of the change, the magnitude of the change. Both the information will be integrated with the spatial allocation. Now spatial allocation will be used to predict and simulate the land is land cover scenario in upcoming future. And now we will validate our model, and if it is not providing you the accurate results, so we need again to go to the selection of the variables and also the selection of the suitable sites or potential sites of the change. And if our model is validated, if it is providing good accuracy, then we will run the model and we will see the predicted information, we will see the simulated information in the near future. So this is the case study showing how we can use LULC information up to time period by incorporating different explanatory variables, by incorporating different socioeconomic different biophysical variables into the model. That model is a spatial allocation of the change, amount of the change and the location of the change. And after getting all this information, after integrating all this information, we can have the simulated information of the LULC class in upcoming time, in upcoming year, and then it will be used to predict and simulate or model our urban growth. Okay, this is the way in which we can have this information. Now moving to the next slide, LULC maps are there. So this is the example where we can have the LULC maps of three time periods: 1988, 2001, 2015. Okay, this is multi-temporal LULC maps, and right now it is having the accuracy of different LULC classes around 86.94%, 88.84%, 89.25%. These multi-temporal LULC maps are having several classes: agricultural land, dense vegetation, sparse vegetation, fallow land, built-up land, water bodies, and sand. Okay. Now moving to the next slide, we are having the area distribution of LULC of years. Wait for a moment, I will get back to you soon.